Now one more problem, problem set 2.6, solution to 2.87, engineering mechanics. So the statement of the problem runs like this: a vertical load, if you look at the original diagram, and this P is a vertical load, it's a weight, supported by a triangular bracket. This load P is supported by a triangular bracket ABC. It's a triangular bracket. This can be made of steel, can be made of wood. Bracket as shown in figure G. Find the forces transmitted to the bolts A and B. There are two bolts, one at A and one at B. And the triangular bracket ABC, which is carrying the load P at the end C. The triangular bracket is supported by the bolts A and B. It is fixed. Assume that the bolt B fits loosely. As you can see from the diagram, the bolt at B is loosely fixed. Means you can shift it to this side. You can shift it to this side. The triangular bracket can be shifted like this or can be shifted like this, since it is not tightened. But the bolt at A is tightly fixed. Assume that the bolt B fits loosely in a vertical slot in the plate. Now, let us analyze the problem. This distance from here to here 150 mm, from here to here is 200 mm. So what will happen due to the vertical load P hanging from this end? This triangular bracket ABC will try to turn like this. Will try to turn like this clockwise. Means there will be some action-reaction forces at point B and point A as well. So I have redrawn the diagram and am explaining. The load P is supported by the triangular bracket ABC. That is, it does not rotate about point B or point A. Supported, it is in equilibrium. Now here we shall find the turning effect of various forces about point A and point B, and we'll make the clockwise torque equal to anti-clockwise, we'll make the torque clockwise moment of the forces equal to anti-clockwise moment of the forces about a given point, and I'll find out the reactions A and reaction at B. So what is to be found out is the reaction force at A represented as RA, the reaction force at B represented as RB. These two things to be found out. Now, the reaction force at B represented as RB acts from C to B. Why this acts from C towards B? Now, due to the load P, and the triangular bracket ABC will try to turn like this. Means at point B, there will be some action force towards the right. And according to Newton's third law of motion, there will be a reaction force exactly in the opposite direction, that is from C to B. And let it be RB. So the reaction force RB acts from C to B. Since it is a guide. Now, if you produce the reaction RB, the line of action of RB to this side, and the line of action of P, they meet at point C, the point of concurrence. So the resultant of RB and P will be to this side. Since it is in equilibrium, therefore the reaction at A should be pointing exactly opposite in the direction opposite to the resultant of P and RB. So from point A, this is the reaction force at point A. Now let us take the turning effect of the forces about point A. Since RA, the reaction at A, is passing through the point A, means RA does not have a perpendicular turns from this point. So RA, the reaction at point A, will not have a turning effect about point A. But the other two forces, the load P and the reaction RB, will have some turning effect about point A. One will be clockwise, the other one will be anti-clockwise. The direction of a P from the point A has this perpendicular distance, 150 mm. So P times this perpendicular distance, 150 mm, about this point, will have a clockwise turning effect like this, that is a clockwise moment. And the direction of RB, reaction at B, RB, from the point A, has this perpendicular distance, that is 200 mm. So RB will have a turning effect about A in anti-clockwise direction. This anti-clockwise moment due to RB about point A should be balanced by the clockwise moment by P about this point for equilibrium. So moment of the forces, so sum of the moments about point A is equal to 0. So P times 150, P times 150, which is a clockwise movement about point A, is equal to RB times 200, which is the anti-clockwise moment of RB about point A. So keep RB on one side, take this 200 to the left hand side, so it becomes P times 150 over 200. 150 over 200 comes out to be 0.75 times P is your one answer. Now, to find out RA, we have to find out some angle, because if you look at RA is pointing to this side. If you draw a horizontal line here, which I have shown it here, let this angle is equal to alpha. So that is RA makes at point A with this horizontal line. So since this is alpha, so this will be your RA times cos alpha, and this will be your RA times sin alpha. So once that is known, so let us find out tan alpha. So tan alpha will be, so tangent tan alpha will be, if you draw this line, this length from C to this point is same thing as from B to A, that is given as 200 mm, and the base from here to here, that is same thing as from here to here, that is 150 mm. So tan alpha is equal to 200 mm over 150 mm. Millimeter cancels, so we are left with 4 by 3 is your tangent of alpha. So alpha is tan inverse 4 by 3. Put it in a scientific calculator if you have, or if you don't have, you can download from the Play Store. Very good scientific calculators are available. Then alpha comes out to be 53 degrees 7 minutes 48.37 seconds of arc. Now, once that is found out, let us take the moment of the forces about point B. Moment, that is the turning effect of forces about point B, right? Now look, this RA sin alpha, the direction of RA sin alpha from the point B doesn't have a perpendicular distance. So RA sin alpha will not have a turning effect about point B, since this does not have a perpendicular distance from point B. Whereas RA cos alpha, which is pointing to this side, and point B is here, there from B to A, which is equal to 200 mm, is the perpendicular distance of RA cos alpha from the point B as the moment center. So RA cos alpha times this length, that is 200 mm, will be an anti-clockwise moment like this. Anti-clockwise moment like this about point B. So RA cos alpha. So RA cos alpha times 200, it is an anti-clockwise moment about point B. and that is balanced by P times, if you look here, the direction of a P from the point B has a perpendicular distance 150 mm. So P times 150 mm is a clockwise movement about the point P. So since it is in equilibrium, therefore Ra times cos alpha into 200 is P times 150. Now we have already found out the angle alpha. So Ra is equal to P times 150 over 200 times cos alpha. Put the value of cos alpha. P is not known, so the answer will be in terms of P. So this comes out to be, if you put these values, 150 over 200 times cos alpha, this comes out to be 1.25. P remains as P, so 1.25 times P is your reaction at point A. At the bolt, which is fixed here at point A, the reaction is 1.25 times the load P, and at B, the reaction RB is 0.75 times the load P, right? Means the reaction at A is more than the reaction at B. Means the place where the knot is loosely tightened at B, the reaction is less, and where here the nut bolt is tightly tightened, the reaction is more. So that is all about. So I hope you like the explanations, and if it really suits you in your engineering examinations in your colleges, give us a thumbs up. You may subscribe it also. Thank you very much. Thank you.